In this video, we shall be discussing about the Ampere circuital law, which is associated with the magnetic effect of electric current. Now, the law states that if we were to consider a conductor carrying current, and there is definitely some magnetic field associated with it. Now, this magnetic field that is associated, if the magnetic field is integrated over a closed loop, the line integral, that is the line integral of the magnetic field, then that will be equal to mu naught times the total amount of current that is passing through that loop. It's not I naught though. Let's keep it as just I. So if you observe, this has similarities with the Gauss law in electrostatics, where you had the electric field taken over a closed surface, and that integral was equal to 1 over epsilon naught. Now, as I had already mentioned earlier, that mu naught and epsilon naught, they are always at reciprocals with respect to one another in their respective equations. Like in case of the constant electrostatic force constant, you have 1 over 4 pi epsilon naught. In magnetostatics, you have 1 over 4 pi, but the mu naught stays in the numerator instead of the denominator. So here we have E dot ds, and that is equal to 1 over epsilon naught times of the total charge that is enclosed by the closed surface. Now, obviously, the current that we are considering over here, the summation of the total amount of current that is we are looking for, that is the total amount of current that is within, or that crosses, or that passes within that loop considered, the closed loop. So for that, if we are considering the current that is flowing along this conductor, let us say that it is moving in the upward direction, the amount of current being I, then we can consider the magnetic field over here, and this magnetic field intensity at this point, it will have some value. We can determine that by using the Biot-Savart's law, and then we can consider a loop, an Amperian loop, to be passing through it, through that point where the magnetic field intensity has been considered, and that is giving me the total loop on which the line integral is being performed. So B dot dl, and the direction of dl is usually along the direction of B, in that case going into the plane as per the given figure. So this is more or less the Ampere circuital law. We can prove it by taking this very example that we have at hand, this illustration. It shows the magnetic field intensity. Now, if you remember correctly, that the Biot-Savart's law had an application related to the magnetic field that is associated with a long straight conductor, and for infinite length we had obtained the magnetic field intensity. So if we were to draw the proof of this, then we will be taking the magnetic field intensity. In that case, it was mu naught I over, well, that is 2 pi a, mu 0 I divided by 2 pi a being the radius over here, the distance of that loop, and in this case the distance of the point where the magnetic field intensity is being taken. Now, as I said, B dot dl is usually along the same line, so we have B dot dl to be equal to B dl cos 0, so that cosine of 0 can be taken to 1, and this integration is over that closed loop which is circular in this case. So this is from 0 to 2 pi a, and guess what, it ends up with 2 pi a, and there's a 2 pi a down there. So what we are going to get is simply the result of the Ampere circuital law. So this is more or less the case that we can consider. Now, the Ampere circuital law again has applications just like the Gauss law in electrostatics, because we are drawing an analogy with that. So as in Gauss law, we had determined the electric field intensity due to various charge distributions. Here as well, because of the current flowing through conductor, the magnetic field associated with them can be obtained. Well, we also had the Biot-Savart's law for sure, but this is again another way of obtaining the magnetic field that is associated with a conductor. Now, in case of straight conductor, we can go the reverse way and obtain this same thing, that is the magnetic field intensity from the total amount of current that is taken within that Amperian loop. So there's no point in doing that again. We'll go to two separate applications, two more applications. This is obviously one of it, but the second and the third case that we are going to discuss are that of the solenoid and the toroid. So let's obtain the magnetic field intensity that are linked with a solenoid and then with a toroid. So this is more or less the arrangement of a solenoid, where we have a wire carrying a certain amount of current to be wound over a given cylindrical arrangement. It may be a non-conducting material, it may be a conducting material, soft iron, maybe soft iron cored solenoid, or even air cored solenoid in case of only air and just the spiraling of the wires. Now this is just to show that the wires have been wound over something, so that you get a nice view of it. Now supposedly what I do is I cut from this exact point, right from the middle of it. I just cut it out. What happens is that we observe now that the cylinder has two points over there, or two sides, two arms, and this is obviously the lower region of the cylinder. I'm going to erase it, but I'm showing you right now. So this is more or less the cylinder which is lying. The top part has been cut off. Now I have just imagined to cut that off, because cutting that out would completely do away with the current. So that's not our case over here. I'm just asking you to imagine that if I cut that top or curved surface out that is facing you, the convex part that is facing you, and all that you have left is the concave part, so that you get a cross-sectional view of the flow of current. Now how do you get that? So if you can now see that there are dots over there, let me just erase those lines that I've just drawn. So there you have dots at the top and a corresponding cross at the bottom, which tells us that the dots tell us that the current is coming out from those points in that given solenoid, and the corresponding cross tells us that the current element, the wire which is wound, that is going into the plane. So as we are observing it, the three-dimensional case in 2 dimensions, this is how we are illustrating it. The dots mark the coming out of the current, and the crosses mark the going in of the current into that plane, winding around that given cylindrical substance. Now we wish to obtain the magnetic field intensity that is associated with this solenoidal arrangement. For that we take this cross-sectional view, this cutout view, and that is quite helpful in understanding the topic. So what we do is we construct a very small Amperian loop. Now the Amperian loop is again just like in Gauss law in electrostatics that we had considered symmetrical arrangements, symmetrical Gaussian surfaces. Here again we'll be considering symmetrical Amperian loops, and as a result of that we'll be considering a very small square loop. So a square loop at this point is what I wish to draw, and that is exactly what I'm doing. So this is more or less a square loop that I'm constructing, Amperian loop. You can magnify it for your convenience. Now this, even if it looks not to be a square, but Let's take it as a square for now. So this square loop supposedly has a length of each side being equal to, let us say, L. So this is L, this is L. Now with those lengths, what we do is we apply the Ampere circuital law. Let's just name those vertices uh, for taking them for proper consideration. So let's just name them. We are naming them as supposedly P, Q, R, S. Now PQRS is that loop where we wish to apply the Ampere circuital law and thereby obtain the expression for the magnetic field that is associated with the solenoid, which is carrying current, which is current of magnitude given as I in that given figure. So what we do is we consider each single segment, the net magnetic field intensity B dot dl over that entire Amperian loop is going to give us mu naught times of the total current that is enclosed by the loop. Now what is the total current enclosed by the loop? If the total amount of current is that is passing through the wire is I. Now with a small segment of the loop considered, obviously the value of I is going to change. We'll see how. But let us first take the B dot dl, the left hand side. Let's tackle that and then we'll move over to the right hand side. So on the left hand side what we have is we take the LHS term, and B dot dl, well, that is simply, that can be taken segment wise, that is B dot dl from, when we are going from, supposedly we are going clockwise, so we will be going from P to Q first, then from Q to R, then I'm writing it down, then from R to S, and finally P dot dl from S to P. That's it. This is the left hand side that we are considering. Now if we observe the magnetic field, the lines of force that will be associated, and if you remember that for a circular coil, now this is obviously, these are circular lines, the circular current carrying coils that we are considering, and from the top the current is coming out, going round, and at the bottom you see the current element entering into the plane. So that means if I align my four fingers of the right hand along the flow of current, the direction of flow of current, what I get to know is that the magnetic field inside the solenoidal arrangement is going to be directed along this direction. So this is the direction of the magnetic field. Now that being the direction of the magnetic field for P to Q, well, it lies along the direction of magnetic field, but the magnetic field is inside the solenoidal arrangement. Outside that, the magnetic field is zero. So that means this entire term is going to be zero, because the magnetic field here is zero outside, because PQ, as you can notice, is lying outside the solenoidal arrangement. So that does not count. B is zero in that case. As for Q to R, the magnetic field is normal to the QR element. So B dot dl is going to end up zero, as B is normal to the QR element. That being the reason over there. As for SR, well, from S to, or sorry, from R to S as we move, it is directed opposite to the magnetic field over there. So even though we get that, but minus of B dl the cosine has gone to 180, that is why we are getting minus. So cos 180 b dot dl, and dl is integrated over here because the length is L, so it is from 0 to L, and here we are getting a result which is minus BL. This is the value. And the last term again, that is perpendicular, the PS segment that is perpendicular to the magnetic field, and so that goes to 0 as well because PS is perpendicular to the magnetic field, direction of PS, that is. So with these terms done and dusted, what we are left with is only BL on the left hand side. Now let's move over to the right hand side. As for the right hand side, what we get is we take the summation of the total current that is enclosed. Now the total current, the current through the wire is obviously I, but how many wires have been considered? Now the solenoid usually has plenty of wires which are wound very close to one another, and we usually consider the number of turns over a unit length because the total number of turns is very huge. So for calculations we usually consider the total number of turns per unit length. So n here is the number of turns per unit length, and as you can see right hand side I have adjusted I made the correction that I have mentioned there, I enclose the total amount of current that is enclosed. Now n is the number of turns per unit length, and what is the length of this element that we are considering? Well, the length extends over the distance L, so the total number of turns which is contained within that is n into L, and that will have I for each turn. So the total number of turns into the current that is associated with each turn is going to give me the total current that is enclosed within that, and mu naught times of that is as per the Ampere Circuital law. Now we wish to calculate the magnitude because we know the direction of the magnetic field over here. So the magnitude wise we can say that B times of L is simply mu naught NLI. The L's get cancelled. It doesn't matter what is the length of the given Amperian loop that we have considered. So all that matters is mu naught times of N times of I, that is the current, as well as the number of turns per unit length. They do play a part in determining the magnetic field intensity. Also what matters is, because we have considered supposedly an air medium or a medium with the permeability mu naught, that is for air or vacuum. In case we consider any other medium with some other magnetic permeability, then what we get is, for any other medium we will be getting the value of B to be equal to mu r times, which is the relative permittivity, sorry, the relative permeability of that medium, mu r times of mu naught N times of I. That is going to give me the net magnetic field intensity which is associated with, for any point which is lying within the solenoid, and within the solenoid that is lying somewhere in between. When we reach the ends of the solenoid, suppose we consider this end or this end, if we are considering the end points of the solenoid, then there's a separate derivation for that, but that will be dealt with in the university level physics that we'll be discussing. So I'm just giving the formula for that. That is exactly half of what we have obtained right now. So this is for that B will be equal to mu naught times of N times of I divided by 2 for each of those end points. So these are the end point value of the magnetic field intensity. Well, you can consider the Amperian loop in that case to be halved. So that's more or less the case that we are taking into account, or in account, to remember this particular formula in case it comes up somewhere. So that's one of the applications of the Ampere Circuital law. The next bit contains that of the toroid. So let's see what we have in case of a toroid. So a toroid is basically, if you consider the ends of the solenoid to be connected, uh, making it a circle instead of a linear arrangement, that is what we get in case of a toroid. So you can refer to the figure over there, more or less the case where we consider a tube, those found in the swimming pools, and the wires wound around the tube. That's more or less a well spaced wiring, but the wiring that we usually get in case of solenoids as well as toroids is pretty concentrated, where we get around 1 turn per centimeter, that is to say 100 or maybe 200 or maybe 300 turns per meter. So that's this is just an illustration to explain this to you. So I have tried to keep those spacing, keep the spacing pretty extended. Now again, what I would like you to imagine is that we again cut the cross section part, the top cross section part, and what we get to see is that with the current entering from the inside and winding along that circular tube, along the body of that circular tube, and then going into the plane, which is marked by the cross signs, which correspond to the dots which indicate the current element coming out, and the cross indicate the current element to be entering into the tube, or going round the tube, entering into the plane as we see it. So I know it's pretty tasking to imagine such things, but I hope with a good physics brain so far you can understand this. Now with this kind of an arrangement, we wish to obtain the magnetic field intensity for sure, and within the toroid, of course. So what we do, instead of considering the square Amperian loop as taken in the previous case, what we do is we consider three concentric circles, and from the three concentric circles, three Amperian loops that is, we will try and obtain the expression for the magnetic field. So first loop as I draw it is the within the inner ring of the tube of the toroid. Okay, and that does not, that is, let's mark that as 1, and that does not carry any current element within it, so that does not count really, but it has to be specified because we are considering the entire toroidal arrangement. Next up, we consider another loop which lies in between the body of the tube, or within the body of the tube. So that is loop 2. And the third loop is completely outside. So this is the third loop. Now with all those three loops, we'll be applying the Ampere circuital law to obtain the expression for the magnetic field. Now this is for the first loop, loop 1, and this is B dot dl, as we know that there is no current that is enclosed within that. That is definitely going to be 0. So for that we are going to get mu naught times of 0, so that is 0. So there is no field present within that region. As for the region 2, we have B dot dl, and that is mu naught times of the total current. The total current in this case again is considered for the entire length of the solenoid, and if the total, so let's just keep it as I, which is enclosed within that ring, the second ring that we see, the second Amperian loop. And as for the third case, B dot dl again is mu naught times of I enclosed. Now, the current that is enclosed within that third loop, I would like to focus on that first. Now, for each current element that is coming out over here, supposedly, let me take another ink for proper marking. So suppose I take this one, this is the current that is coming out of the plane, and the corresponding current element that is going into the plane. So both those current elements considered within the loop, the directions, they cancel out each other, one positive, the other negative, just as in case of charge, the positive and negative charge being placed within the given enclosed surface, the net field or the net flux that would have been associated or linked goes to zero. So is the case over here with the current, one of the current elements coming out and the other going in. They equate to zero. The summation equates to zero. And the same case goes with the rest of the elements that are present within that third loop that we have considered. So in this case as well, the total enclosed current is going to zero. So this entire thing is going to zero as well. So all that we are left with is the second loop, and in the second loop, the current elements that are going into the plane, that is outside the outside surface of the tube, they lie outside that second loop that is considered over here. So the only elements that are present are those inside which were coming out, the dots. The crosses lie out of it, the dots lie inside. And if we are considering n number of turns over here, so we have total number of turns to be number of turns per unit length, that is n, and the total circumference is the total length, so that is 2 pi. Let the radius over here be equal to a, let the radius be a. So we have n times of 2 pi a, and the current across each ring is going to be I. So n times of 2 pi a times of I. Let's see what we have on the left hand side. In the left hand side we have b dot dl. Now b and dl, they are going along the same direction. So b dot dl is going to be taken integrated over that entire length, so that is 2 pi a as well. So finally what we are getting is 2 pi a's, they cancel out each other, and the magnetic field therefore B is equal to mu naught times of n times of I, which is the same as that obtained in case of the solenoid. So the expressions of the field intensities within the solenoid as well as that in case of the toroid are the same, exceptions being that the end points of the solenoid having half of that value, but there are no endpoints in case of toroid. So the toroid has is going to have the magnetic field associated with it to be mu naught times of Ni, and that lies inside it. Outside it is 0, and inside of the inside, that is if we consider that tube, that inside point over there, there the magnetic field is going to be 0, there the magnetic field is going to be 0. The only magnetic field that is going to lie is within that tube region. Once again, if we are considering an air cooled toroid, we are going to get mu naught times of Ni. Whereas if we are considering any other material with some other magnetic permeability, then the expression is going to be of the form that I've just ticked down, that is B is equal to mu naught mu r n times of I. So that's all from this video. We have discussed the Ampere circuital law. There are various numerical valued problems associated with it. You can have a glance I'll try to provide you with some. Till then, thank you for watching.